So my first attempt at building a memory cell almost worked. Okay, I designed my store pulse to be wide enough that the duration of the pulse was much larger than the RC time constant, R on times C, and so that writing of the capacitor worked well. But the problem was that the storage node here, okay, the storage node here was directly connected to the output, and that was not particularly nice. Okay, this storage node here is my crown jewel. Okay, I can't expose my crown jewel to the outside world because depending on the resistance it was connected to, that value would discharge. Okay, it simply does not work with my memory cell abstraction. The memory cell abstraction was such that I want to be able to read the value of the memory, but the read should not cause that memory value to discharge. Okay, so here's my second attempt. Okay, so what I'm going to do is the problem was that when my output was connected to the load directly, the load caused the output to be discharged. So the obvious thing that comes to mind is, why don't I buffer the value? Okay, so what I'm going to do is I'm going to put a pair of inverters, okay, so that they behave like a buffer. Okay, so if this value is let's say x, if this value is x, then this value is x bar, and this value is again x. Okay, so this becomes my D out. Okay, so together these things form a buffer. So does that work? Okay, let's try to understand this. Will this circuit work? Okay, if I built a buffer here, then this buffer is going to decouple the output from the input. So the output ends up going to some load RL. I couldn't care less. I, as the capacitor, couldn't care less. And the reason was I was decoupled from the capacitor by those buffers. Decoupled from the load by those buffers. Okay, so in this situation, let's go ahead and find out how things work. Okay, let's start by figuring out how long the capacitor can store its charge. Notice that the store pulse width stays the same. Those dynamics haven't changed. So to find out how long I store my charge, let's assume that the resistance looking in here is R in. Now in an ideal world, in a completely ideal world, the resistance looking into our inverter was infinity. Okay, in a completely ideal world. And the resistance into this terminal of the switch was also infinity. But let's say in a practical world, there is going to be some resistance. Okay, there could be the parasitic resistance between this wire and ground. There's some parasitic resistance. There could be some parasitic resistance of the switch, and there could be some teeny resistance that is seen into the gate. Okay, some non-idealities here and there, and let's say that resistance is Rn. So let's assume it's a really huge resistance in the giga ohms, okay, in the billions of ohms, very tiny, a very huge resistance. Okay, so let's assume the input resistance Rn is known. Okay, so that is a huge resistance. So under those conditions, let's try to find out what the duration for which the voltage Vc is such that I store a valid one. Okay, remember again, the governing equation is given by, this is Vc, this is Vs, and this will discharge, and at some point it hits VOH. So this duration here is T valid. Okay, so what is T valid? Okay, we just computed it earlier, just that the time constant is different now. So we computed T valid a second ago, where T valid was given by the time constant minus, in this case, the time constant is Rn C. It's not RL any longer. It's Rn C natural log of VOH divided by Vs. Okay, and this may be 5 volts as an example. Okay, generally Rn is much bigger than RL. Because RL relates to whoever was going to read the value of the memory cell. Okay, and we don't have too much control of who's going to read it. Okay, so if I build a little memory and I sell it on the market, then who knows how people are going to design the circuits to read the memory cell. Okay, I have little control of that. So now, by putting a buffer here, I get Rn, and by making Rn much larger than RL,